You must have one heck of a computer to keep all of these programs running without crashing.
uh, Not really. It has a few times, a couple of times, it has actually, I don't know if crash is the right word, but stop working or start slowing up.
Mm-hmm.
And then I have to close a lot of stuff. It's just a bad habit I have of just keeping things open. I have this feeling that I may need to
Ah.
go back to whatever web page I was on before, whatever. Anyway,
Mm-hmm.
so let's see here. So as I was saying, we were talking about Lewis structures, and we talked about some related. We went through these rules first. We haven't done any examples yet. In fact, that's one of the things we're going to talk about today. But let me go to full screen mode. Right. So we talked about formal charge, the concept of formal charge, which will become important when it comes to drawing the Lewis structures of molecules and ions. We're going to see how that plays in as well. Um, and then we talked about certain molecules that do not obey or follow the octet rule. We're going to see some more examples of that as we go along. But I highlighted these here, a couple of situations where an atom may have less than 8 electrons on its outer shell or can have more than 8 electrons on its outer shell. And if you recall, I said that the atoms that will display this particular property are atoms that are in period 3 and beyond, period 3, 4, 5, etc. All right. Um, I think we talked about electronegativity, just in case I haven't. This is the definition of electronegativity. It's basically a measure of the ability of an atom to attract bonding electrons to itself. And what you'll find is that the electronegativity increases going from left to right of a period and going from bottom to top of any group. All right. And we have some electronegativity values. This was based on a method discovered by Linus Pauling. So he came up with a 4-point scale for measuring the electronegativity of different elements. And this is basically the result. All right. So this is a table that you'll have access to in order for you to use this to determine certain aspects of bonds, including polarity and so on. Okay, so with that said, okay, let me not go into the bond type yet, because I think it's important that at this juncture, we look at some examples of molecules. How do we determine the Lewis structure molecules, right? So I'm going to work through a couple of examples so that you understand how we do this. So the first example we're going to do is this molecule, carbon tetrafluoride, all right? So let's say you're given this molecule and you're asked to determine the Lewis structure for this molecule. So the first step in this process is that you determine the total number of valence electrons. And we all know how to do that. Basically, you go to the periodic table and you look up the group number of the specific elements, and then you add them up according to the formula. So in the case of carbon, if you look that up, you see that carbon is in group 4A. So therefore, it has 4 valence electrons on its outer shell. In the case of fluorine, if you look it up, you see that fluorine is in group 7A. So we have 7 for the valence electrons, but because we have 4 of them, we have to multiply that by 4. So that gives you a total of 28 electrons total, all right? So when you add these up, you're going to get a total of 32 electrons, which is equal to 16 pairs, all right? The next step is that we arrange these atoms in a skeletal fashion where the less electronegative element, which in this case would be the carbon, will be placed in the middle, and we surround it with the fluorine atoms, right? So it doesn't matter how you arrange it, because for now, we're not concerned about the shape. We just want to establish how the atoms are linked to each other, right? So this would be the arrangement, the carbon in the middle surrounded by the 4 fluorine atoms, all right? And then we start assigning the pairs of electrons. Now remember, we have 16 pairs to assign. The first 4 will be bonding pairs between each fluorine atom and the carbon, like this, 1, 2, 3, 4, right? So we have used up 4 of the 16. So the question now becomes, where will the other or the rest of the pairs of electrons end up? And the answer is you start placing them on the surrounding atoms. So the 5th electron could go here, 6, 7, no, what am I saying? Yeah, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that is basically it. That would be the answer, all right? That would be the Lewis structure of fluorine. Now, one thing you should do always when you're determining the Lewis structure of anything is to determine the formal charges. Now, in this case, I know already that the formal charges for all the atoms will be equal to 0, but that will not be true in all cases. So let me just show you how we calculate the formal charges for each atom in this particular molecule. I'm going to start off with the formal charge of carbon. Now remember, the formula for formal charge, I gave you that formula last time. Let me just squeeze it right here. Formal charge for any atom is equal to the group number minus half the number of bonding electrons minus the number of non-bonding electrons, all right? So that's a formula that you're going to apply to each atom in this structure. So in the case of carbon, the group number is 4, we know that already, minus half the number of bonding electrons. So we have to look at the structure and determine how many bonding electrons are present. And what you'll see is that you have 2, 4, 6, 8 electrons. Remember, each line represents a pair of electrons. So we're going to put half 8 here. And then the next thing is the number of non-bonding electrons, which if you look at the carbon here, there are no lone pairs of electrons. So therefore, that would be 0. And when you work this out, 4 minus half of 8, that works out to be equal to 0. So therefore, there are no charges present on the carbon atom, all right? We do the same thing for the fluorine. And you'll notice that each fluorine atom has the same electronic arrangement, right? So therefore, this calculation I'm about to do will be the same for each fluorine. So the group number for fluorine is 7, minus half the number of bonding electrons. So for each fluorine, the number of bonding electrons is 2, right? Minus the number of non-bonding electrons, which would be 2, 4, 6, so minus 6. And this will work out also to be equal to 0, right? So the formal charge on each fluorine atom will be equal to 0. So therefore, this would be the final structure that you're going to write down to represent this molecule, which is carbon tetrafluoride. All right? Okay, any questions about this example? Are there any questions?
No, I don't think so.
Okay, so let's move on now to an example. Let's look at this molecule, PCl3, all right? So we go through the same steps as we did before. Start off with determining the number of valence electrons. So phosphorus would contribute how many electrons? If you go to the periodic table, you'll see that it contributes 5 electrons, right? And then chlorine is in group 7, so it will contribute 7 electrons, but there are 3 of them, so we have to multiply this by 3. So this gives you 21 electrons, and therefore the grand total of electrons would be 26, which would be equal to 13 pairs, all right? So we put the phosphorus in the middle, surround it with the chlorines because phosphorus is the less electronegative element between the two. And then remember now we have 13 pairs to assign. 3 of them will be bonding pairs between the phosphorus and each chlorine, all right? Then the next step is we put the the next pair of electrons we put on the surrounding atoms. So the 4th pair could go here, 5, 6, 7, 8, 9, 10, 11, 12, right? So far we have assigned 12 of the 13 pairs. So the question is, where will the extra pair end up? And it will end up on the phosphorus atom, all right? And again, if you were to calculate the formal charges, you're going to see that the formal charges would be equal to 0 for all the atoms. In fact, let me do that here. So the formal charge of the phosphorus would be 5 minus half of 2, 4, 6 bonding pairs, or bonding electrons, I should say, minus the lone pair here, right? Which is 2. So this gives you a total of 0 because 5 minus 3 minus 2 gives you 0. And we do the same thing with the chlorine, would be 7 minus half of 2 minus 6, and that will give you 0 as well, all right? So therefore, there are no charges present in this atom, or in this molecule, I should say. All right. Okay. Any questions about this one? Any questions? Okay. Let's look at another example. You guys can do this one without my help. H2S. So what would be the first step in this process?
Well, you would figure out how many electrons there are.
Okay, so what would be the number of valence electrons for sulfur?
For sulfur, let's see, 6.
Okay, and what would be the same for hydrogen?
2, because one
Right.
each, and then there's 2 of them.
Okay, good.
So
So the total number of electrons here
that's
would be 8, which would be 4 pairs. All right. So
Mm-hmm.
what would be the next step?
Drawing a skeleton.
All right. So
And
what would that be?
well, we know that hydrogen atoms are always terminal, so
Okay.
logically you would have sulfur in the center and 2 hydrogen atoms on it.
Okay, good. And then what?
Then you would start counting up electron pairs. So we've already got 2 of them.
Where will those 2 go?
And between the hydrogen atoms and the sulfur atom.
Okay.
So that's two pairs, and I guess you would put the other 2 pairs on the sulfur.
Exactly. Because of course, as you correctly said earlier, the hydrogens are always terminal atoms, so they cannot accommodate any more electron pairs. So therefore, you're right, the 2 electrons, the 2 extra pairs of electrons will end up on the sulfur atom. All right. Okay. Anybody has any question about this one? Any questions about this one? Okay. All right. So the next one we're going to look at, a bit different from these, because in this case, oh, by the way, again, before I move on to the next example, again, as practice, you should also calculate the formal charges, right? I won't go through that, but you can try it on your own. Again, the formal charges will be 0 for all the atoms involved in this case, but I won't go through that right now. But you can try that on your own, all right? Okay, now, the next example are different from the ones that we have done so far, because in this case, you're going to see where the formal charges will make a difference, all right? So the molecule we'll be looking at here is carbon dioxide, CO2, all right? So the first step would be what?
Let's see, is my microphone on? Okay. It would be determining the number of electrons. So C has 4. Oxygen has, that'll be 6, plus times 2 oxygen atoms, that's 12, for a grand total of 16 electrons and 8 pairs.
Okay, good. So therefore, carbon in the middle, surrounded by the oxygen, right? So the next step would be what?
Then we would, well, we would draw the lines in between. That's 2 bonding pairs. So still got 6. Draw 1 on each. 1 on each oxygen atom. That's got us down to 4.
Well, basically, you're going to put the lone pairs on the oxygen atoms, the remaining 6, right? So each atom will end up with 3 pairs, and that will be it, right? So you have used up the 8 pairs.
Wait. But where are the unbonded pairs on carbon?
No, there's none. There's none. Because we have used up all the pairs, 8 pairs, right? 2 of them would be bonding here and here, right?
Yeah.
And then here we have the non-bonding pairs, 3 here and 3 here.
So the carbon atom will have a charge of +2?
Yeah, we're going to get to that, right? But I want to make sure that we understand what's happening here, right? So yes, the formal charges is what's the next step, right? So we need to calculate the formal charges for all the atoms involved. So in the case of carbon, using the formula I gave you before, it would be the group number, which is 4 for carbon, minus half the number of bonding electron, which would be 2 plus 2, 4, right? Minus 0, because carbon has no non-bonding pairs, right? So when you work this out, you're going to get plus 2, as you correctly said, right? And then we're going to do the same thing with the oxygen. Remember, the calculation for one oxygen is the same as the other because they have the same amount of electrons bonding and non-bonding. So the group number for oxygen is 6 minus half the number of bonding electrons, which is 2 in the case of the oxygen, minus the number of non-bonding electron, which is 2, 4, 6. And this works out to be equal to minus 1, right? So let me just erase some stuff here to avoid confusion. Oops. Okay, why is this not erasing? Let me erase these here. Okay, so based on what we have done here, the charge on the carbon is plus 2, right? And the charge, excuse me, on each oxygen is minus 1 here and minus 1 here. Now, when we have a situation like this, where you have an atom which is positively charged, directly bonded to 2 atoms which are negatively charged, then we'll try to get the charges canceled out. And the way that is done is that in the case of the oxygen here, this pair of electrons will move here to form an extra bond. When that happens, this negative charge will cancel out one of the 2 plus charges, right? And then this pair of electrons will come here to form an extra bond, which means that this negative charge will cancel out the remaining plus charge. So therefore, the final answer in this case is so that would be the Lewis structure of carbon dioxide. All right. So this is one of those structures where it is absolutely important for you to determine the formal charges so that you can see which charges will cancel out to get the final structure. All right. Okay. Any questions about this particular example?
I do. Why wouldn't there just be two unbonded pairs on the carbon atom?
Because when we were in an earlier stage of this exercise, when we were assigning the electrons, right? Remember the order is this. You assign the bonding electrons first, right? Then you start putting pairs of electrons on the surrounding atoms.
Surrounding, okay.
Exactly. And then if there's any more left over, you start placing electrons on the central atom. You see what I'm saying? So it's bonding first, right? Then you start placing electrons on the atoms surrounding the central atom. And then if you have any more left over, then you start placing them on the central atom.
Yeah, this makes a lot more. Yeah, this makes a lot more sense than in introductory chemistry. I was just kind of guessing about the
you have to follow that order. And the reason why is that they after putting the bonding pairs, the reason why you put the electrons on the surrounding atoms because those atoms are the more electronegative ones. You see what I'm saying? So they are more likely to get the electrons first before any other atom. You see what I'm saying? So that's why you place electrons on the surrounding atoms, and then if you have any more left over, you place them on the central atom.
I see.
Right?
All right, that makes sense.
Okay. All right. Here. So any other questions about this? Anybody? Any other questions? Because it's important that you understand the logic that you'd have to follow in order to, determine the Lewis structure if you're given a molecular formula. Okay, so if there are no other questions, let me remove this and commence to this one here. SO3. Okay, so the first step would be what?
That would be figuring out the number of electrons, which is 6 for sulfur, and 6 each for oxygen.
So that gives you a total of 18 electrons from the oxygen, and therefore 24 electrons total, which would be equal to 12 pairs, all right? Then we put the sulfur in the middle, surrounded with the oxygens, right? So we have 12 pairs to assign. So 1, 2, 3, those are the first 3 pairs, bonding pairs. Then 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. So the next step would be the formal charges. So in the case of oxygen, the formal charge would be equal to the group number, which is 6 minus half of 2, right, minus 6. So this gives you minus 1. So each oxygen is going to have a minus 1 charge. And then we do the same thing with the sulfur, which would be 6 minus half of 6 minus 0, because there are no lone pairs on the sulfur. So that's why we have the 0 here. So when we work this out, you're going to get plus 3 here. So this will be equal to plus 3 for the charge, all right? So in this case, we have 3 negatively charged oxygen atom bonded to the sulfur atom, right? Which is positively charged. So what's going to happen in this case is something similar to what we saw in the previous example, where this pair of electrons will go here. So this negative charge will cancel out one of the 3 plus charges. This pair of electrons will go here. Same thing will happen. Negative charge will cancel out the remaining one of the 2 remaining plus charge. And therefore, this pair of electrons will go here. And that negative charge will cancel out the remaining plus charge here. So therefore, the final answer is going to be S double bond O, lone pair, double bond O, lone pair, double bond O, lone pair. And this would be the final answer. All right, so that's the Lewis symbol for sulfur trioxide.
All right.
Any questions about this one?
Nope, not I.
Okay, so let's look at another example. Let's look at this one, SOCl2. All right, so again, what we do is determine the valence electrons. So sulfur will contribute 6, oxygen will contribute 6, and chlorine each will contribute 7, but we have to multiply by 2. So that gives you 14. So that gives you a grand total of 14 plus 6, 20, 26 electrons, which would be equal to 13 pairs. All right. So in this case, we put the sulfur in the middle and surround it with the oxygen and chlorine atoms. We have 13 pairs to assign, 3 of which will go here, here, and here. Then, because oxygen is more electronegative, I would start placing electron pairs around the oxygen. And when I say more electronegative, I mean compared to the chlorines, right? So I would put 3 pairs of electrons here for the oxygen. So that's a total of 6 so far. Then 7, 8, 9, 10, 11, 12. So the 13th pair will end up on the sulfur, right? Then we need to calculate the formal charges. Let me see if I can squeeze that down here. So let me start off with the sulfur, right? So in the case of sulfur, it would be the group number, which is 6, minus half the number of bonding electron, which would be 2, 4, 6, minus the number of non-bonding pairs, which would be 2. So that's 6 minus 3 minus 2. That gives you plus 1. So there will be a formal charge of plus 1 on the sulfur. And then we do the same thing for the oxygen. 6 minus half of 2 minus 6. And that would be, so this is plus 1, and this would be minus 1. And then finally, in the case of chlorine, it will be 7 minus half of 2 minus 6, and that gives you minus 1. I'm sorry, that gives you 0, right? So basically, the oxygen has a minus 1 charge. There are no charges on the chlorine, and the sulfur has a plus 1 charge. So what do you think is going to happen in after this?
We're going to have a double bond on the sulfur and oxygen.
Exactly. This pair of electrons will come down here, The negative charge will cancel out the plus charge, and therefore your final answer is going to be S double bond O, Cl, Cl, and lone pair of electrons here. So that would be the final answer. All right?
Okay.
Okay, any questions about this one? Any questions?
Nope.
All right, so let's move on to something a bit different again. So the example we're going to look at here. So what we'll be looking at now are polyatomic ions, right? So these species will carry a charge. So the way we deal with this is slightly different compared to what we were looking at before. So here's the first example, CO3 2 minus, right? So in this case, like we did before, we would look up the group number of carbon, we'll see it's 4. We look up the group number of oxygen, we see that it's 6, multiplied by 3, so that gives you a total of 18. But we now have to take into account the fact that you have 2 negative charges. So the way we do that is that for each negative charge, we add an electron to the total, right? For each negative charge, we add an electron to the total. So since we have 2 negative charges here, we're just simply going to add 2 electrons, right? So therefore, the answer in terms of the total number of valence electrons would be 24 electrons, which would be equal to 12 pairs, all right? So put the carbon in the middle, surround it with the oxygens, all right? And then we have to start off by putting the bonding pairs, 1, 2, 3, all right? Then 4, 5, 6, 7, 8, 9, 10, 11, 12, all right? So now that we have assigned the electrons, we can now calculate the formal charges. So for carbon, based on the formula, that will be 4 minus half of 6 minus 0. And this will give you 4 minus 3, so that will be plus 1. And then for each oxygen, it will be 6 minus half of 2 minus 6 equals to minus 1, all right? So each oxygen here will have a minus 1 charge here, here, and here, while the carbon will have a plus charge, all right? Okay, so what do you think is going to happen after this? Here we have 3 atoms, 3 oxygen atoms that are negatively charged, and they're all bonded to the same carbon, which has a plus 1 charge. So what do you think is going to happen in this case?
I think you would probably have a double bond that would switch between atoms.
So in other words, it doesn't matter which one. So I'm just going to do this one right here, right? Okay. So therefore, what that means is that this negative charge is going to cancel out this plus charge, right? So therefore, the final answer becomes C double bond O, lone pair, O minus O minus. And that will be the final answer, all right? And please note that in the final answer, you have these 2 negative charges here, right? Which corresponds to the 2 negative charges in the initial structure or formula that you were given, all right? So that's one thing you should look out for when you're dealing with polyatomic ions. In your final answer, the number of charges present in your final answer should be the same as the number of charges present in the formula that you're working from. All right? Okay, any questions about this one? Any questions? Any questions? Okay, so let's look at this one. Okay, the phosphate ion, PO4 3 minus. Okay, so what would be the first step?
Let's see here. That would be, well, count up the number of electrons. So for phosphorus, that would be 6. No, that would be 5. For oxygen, that would be 6 each. And how many? Oh, that's a 4. Okay, so 24. Yeah. Then that would be 29, then we would add 3 electrons and give us 32 electrons with how many bonding pairs of that? That would be 16 bond. Oh, yeah.
16 pairs, right. So we put the phosphorus in the middle, surround it with the oxygens. All right. Then what? Bonding pairs, right? 1, 2, 3, 4, right?
And then I guess we start putting unbonded pairs around the oxygens.
Okay, so 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right. Okay, so let's do the formal charge calculations, starting with the phosphorus. So how would you calculate the formal charge for phosphorus?
Okay, so the group number is 5. There are -1/2 times 8. Bonding electrons is 4 minus 0. So that gives us a +1 charge.
Okay, very good. And then for the oxygen,
6 minus 6 minus 2. No, half.
No, minus half of what?
Yeah.
Minus half of 2, right?
Yep. Which is 1 minus those are 6 unbonded pairs, so that gives us a -1 charge.
Okay, so each oxygen, so the phosphorus has a +1 charge, and each oxygen will have a -1 charge. All right. Okay, so what do you think is going to happen from here?
Then from one of the oxygen atoms, we'll move an unbonded pair into a double bond.
Okay, so let's move that one. So the final answer is going to be P, double bond O, single bond O with a minus charge here, single bond O with a minus charge here, single bond O with a minus charge here. All right, and that would be the final answer. And again, please note, the total number of charges present when you add them up will be equal to the total number of charges in the original formula of the, in this case, ion that you're starting from. All right? Okay. Any questions about this one? Any questions? Any questions? Okay, so here is another example, and I'm willing to bet that you guys will screw this up if you try it. The nitrate ion.
All right.
The nitrate ion. Okay, so let's do this. First step.
That is group number 7.
Nope.
Nitrogen. Nitrogen. No, that's group number 5. Whoops.
Okay.
So 5 electrons from there. Oxygen is 6 times 3, which is 18, plus an extra electron is totals. Let's see, that'll be 24. 12 bonding pairs.
So nitrogen in the middle, oxygen, oxygen, oxygen. Okay, so what next?
Then I guess I'm gonna start putting non-bonding pairs on. So 1, 2,
no, bonding
3.
pairs first.
Yes, bonding pairs. 1 between each, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right.
1, 2, 3, 4, 5, 6. Well, actually, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, very good. Okay, so.
And then the group number 5 minus.
Okay, hold on. So we're talking about formal charges, right?
Yep. Formal charge of nitrogen is 5
nitrogen.
minus half of 3.
Nope.
No,
6.
3, 6.
Right.
All right. Minus 3 minus. There aren't any unbonded pairs.
Right.
So that'll give us a charge of +2.
Okay,
now for
very
each
good.
oxygen, 6 minus 2. No, not 2. Half of 2, which is 1, minus 6 unbonded pairs, or 6 unbonded electrons, which gives us -1.
Okay.
All right.
So the nitrogen has +2, and each oxygen has -1. All right. Okay. So what next?
Well, as far as I can tell, it looks like we're going to have 2 double bonds.
Wrong.
A trip.
I knew.
So this is going to be a triple bonded.
Nope.
This is going to.
Nope.
No?
What you're suggesting is this, right? You're suggesting this pair goes here, and another pair goes here. And I understand fully the reason why you said that, because you have a +2 charge here, so you'd expect 2 negative charges to cancel the 2 plus charges, right? Now, the reason why it won't work is because of something I said last class. If you were to do this, right, you're going to end up with a double bond here and a double bond here. That would result in nitrogen having more than 8 electrons on its outer shell, which is impossible for nitrogen. Nitrogen can't have more than 8 electrons on its outer shell. Because, remember I said that the only elements that can have more than 8 electrons on its outer shell are elements from period 3 and below. Nitrogen is in period 2. You see what I'm saying? So nitrogen cannot have 8 electrons on its outer shell. So what's going to happen? Let me erase this here. What's going to happen is only one of these double bonds will be formed. Erase this here. I do this every semester and students fall for it every time. Okay, so the final answer, well, actually, let me do this. So the final answer is gonna be O double bond end. Now here, the 2 plus charge will be reduced to +1, all right? And then this will be minus, and this would be minus. So this would actually be the final answer. You see what I'm saying?
So so the net charge results in just a -1 charge.
Exactly. Because when you add up, basically in this final answer, you have 1 plus charge and 2 negative charges. So therefore, the net result is -1 charge, which is the original charge in the structure right here. All right?
I see.
So that's basically how that is done. All right? So you have to be careful about all these things. You have to take into account whether or not an atom can have more than electrons. So you need to remember that only elements in period 3 and below, periods 3, 4, 5, 6, and 7, can have its octet expanded.
So if we replace nitrogen with phosphorus, there could be 2 double bonds?
Yes, absolutely right. So in the case of the phosphide ion, I think it's called, the final answer would be, you know what, let me clear this. So the final answer would be P double bond O, double bond O, double bond O. Right? And that's because phosphorus can have more than 8 electrons on its outer shell.
But it only has a +2 charge. So there would only be 2 double bonds, right?
Hold on. Oh, my bad. I'm thinking of something else. You're right. So let me erase this here. You're absolutely right. And then you're right. There are only 2 double bonds, and then this, and then negative charge. Right. That would be the structure of the slide. Yeah, exactly. Okay. Any other questions about that example, which I erased, unfortunately? The nitrate ion.
Nope.
Okay. Let me do another one. Now, this one is an example of a cation. CBr3 with a plus charge, right? So in this case, carbon will contribute 4 electrons, and each bromine will contribute will contribute 7 multiplied by 3 equals to 21. But now you have to take into account that you have a plus charge here, which means that we do the opposite of what we did when it comes to the anions. We subtract an electron for each charge, each plus charge that is present, right? So in this case, it's going to be 24 electrons, which is equal to 12 pairs, all right? So we put the carbon in the middle, surround it with the bromines, and then, like before, we put the bonding pairs, then we put pairs around the bromine, so 4, 5, 6, 7, 8, 9, 10, 11, 12, all right? Then we calculate the formal charges, so the formal charge for, let me see here, the formal charge for the bromine is, bromine
that'll be,
would be 7 minus half of 2 minus 6, which will give you 0. And the formal charge of carbon would be 4 minus half of 6 minus 0, which gives you 4 minus 3, so plus 1. So basically, carbon has a plus 1 charge, and there are no charges on the bromine atom, all right? So basically, this would be it as far as the Lewis structure of this particular ion is concerned, right? Now, later on, we're going to learn about a concept known as resonance, which would allow for this pair of electrons to go here, right? To form this structure. I won't go into the details of resonance. Now we're going to talk about it later on, right? But the thing that will happen as a result of that movement of electron pairs is that this bromine now will now end up with the plus charge. So when this pair of electron goes here, right, this plus charge here will be canceled out, but a plus charge will appear on the bromine atom right here, right? So that's basically, but that's for later on. That's for the discussion of resonance. Okay, so I thought it was important that we went through these examples so that, you know, you guys get a good feel for how we go about, you know, solving problems of this type where you're given a Lewis structure. You know what? I just thought of another example. Let me do that one before we move on to the next topic. Any questions about this before I erase this? Any questions? Any questions? Okay, so let me just thought of one example here. NO2 plus. All right. So the first step would be what?
Calculate the number of electrons. That would be 5 for nitrogen, 6 times 2, 12 for oxygen,
And for the
minus
charge,
1
right?
Yeah, minus an electron. That would give us
16.
28.
No.
16.
Yeah. 12 plus 5, 17 minus 1.
Oh, I'm sorry. Whoops. Wrong thing.
Okay, so we put the nitrogen in the middle, surrounded with the oxygens. Then what? Bonding pairs first, right? 1, 2, then 3, 4, 5, 6, 7, 8.
6, 7. All right.
Okay, so formal charges. What's the
formal charge of
nitrogen?
Nitrogen, that would be, so group number 5 minus half of 4 is 2 minus 0, which gives us a +3 charge.
Very good. And then for the oxygens?
Oxygens, 6 minus half of 2 is 1 minus 6, which gives us a -1 charge.
-1. Okay, so the nitrogen has +3, and each oxygen has -1 here and here. All right. So what do you think is going to happen from here?
2 double bonds, and then nitrogen will be the atom with the plus charge.
Exactly. So this would be the final answer. Plus charge. All right. So that's basically how that is done. All right. So I think we have done enough examples So based on what we have done here, you should be able to determine the Lewis structure for pretty much any molecule or any ion, all right? Okay, going back to the PowerPoint. So we were talking about electronegativities, and the electronegativity can have some influence based on, well, some influence on the type of bonding that takes place between two atoms, all right? Now, consider this. If you have two identical atoms, right, bonded to each other, for example, in the case of the oxygen molecule or in the case of the nitrogen molecule, right? What you'll see is that both atoms, because they're identical, they will have identical attraction for the shared electrons, right? So the electrons will be evenly shared between those atoms, right? So we call those bonds nonpolar covalent bonds, right? They're covalent bonds because we have electrons being shared between them, and they're nonpolar because basically the electrons are shared evenly between them, equally, right? So you won't have a great attraction for the atom, or for an atom, well, an atom will have for an electron or electrons being shared between itself and another identical atom, all right? So the bonds, like, for example, in the case of nitrogen, in the case of all the diatomic molecules that we learned about, the elements, iodine, fluorine, bromine, chlorine, nitrogen, oxygen, and hydrogen, those bonds are all nonpolar covalent because the two atoms that are bonded to each other are identical, right? So here's the chlorine example, right? Two identical atoms having equal attraction for the shared electrons. So therefore that bond is considered to be nonpolar covalent, right? And as I said before, all the elements that exist as diatomic molecules display basically the same idea with respect to the bond being shared between the two atoms. They're all nonpolar covalent bonds, all right? Okay, so that's one type, right? Now, another type is where you have the electrons being shared unevenly, right? In other words, you have two different atoms sharing a pair of electrons, or more than one pair actually, and one atom is more electronegative than the other. What that means, therefore, is that the more electronegative atom will have a greater pull on the shared electrons. And what that means, therefore, is that the shared electrons would be, on average, closer to the more electronegative atom compared to the other atom, all right? So one example of this is hydrogen chloride, which is a gas, right? Chlorine is more electronegative than hydrogen, so therefore the electrons that are shared here will be, on average, be closer to the chlorine atom compared to the hydrogen atom. And we can represent, so this bond is said to be polar covalent, all right? And we can represent the direction of the shift by using this symbolism right here, an arrow with a cross at the tail. So basically this is showing you where the electrons are shifting to. Another representation that is very often used is this representation here. This delta, this is a Greek letter, all right? And in this context, it represents partial. So what we're saying here is that the chlorine atom in this molecule will have a partial negative charge, while the hydrogen atom will have a partial plus charge, right? It's a partial charge and not a full charge because you don't have a complete separation of the ions. Basically, the atoms are still bonded to each other, but the electrons on average are closer to the chlorine, and therefore the chlorine will have an accumulation of charge. And that is represented by this here, delta minus, whereas the hydrogen will be electron deficient partially, and therefore we have a delta plus symbolism for that, right? So that's what we mean by a polar covalent bond, one where there is a separation of charge such that one end of the bond is partially negative and the other end is partially positive, all right? Now, you can have a situation where the difference in electronegativity is so large that the electrons may be completely transferred from one atom to the next. And in that case, the type of bonding that exists will be an ionic bond, right? An ionic bond is what happens when you have electrons transferred from one atom to another, forming charges, and the force between the charges would be the ionic bond, all right? So a good example of this is sodium chloride. Sodium is the metal, very well, it's not electronegative, has a very low electronegativity value. Chlorine, on the other hand, is to the other extreme. So therefore, in this case, you'll have the complete transfer of electrons from the sodium to the chlorine to form sodium ions and chloride ions, all right? So those are the three categories of bonds when it comes to looking at the electronegativity values. So this begs the question, well, before we get to that question. So this diagram here basically is showing you the difference between a nonpolar covalent bond, where the electrons are evenly shared, and a polar covalent bond, where you can see that the chlorine will have a greater electron density compared to the hydrogen. And this here is called an electrostatic, what do you call it? Electrostatic map of the molecule. It's basically a computer simulation where the red represents negatively charged atoms and the blue represent positively charged. So this is basically another representation of the hydrogen chloride molecule. Clearly you can see that in this representation here, the chlorine is what gets the bulk of the charge, and the hydrogen would be, I'm sorry, the chlorine gets the bulk of the negative charge, and the hydrogen would be electron deficient and therefore will have a partial positive charge. All right. Okay, so I was saying, this begs the question when we talked about the different types of bonds. How do we, how should I put this? How do we determine whether or not a bond is polar, nonpolar, or ionic? All right. And there are different criteria that is used. The ones that we're going to use is what I'm about to describe here. Let me just create another. Let me just do it on my writing pad. So this is the criteria that we're going to use. I'm going to construct a very small table. In one column, you're going to have the difference in the electronegativity values. And in the other column, oops, you're going to have bond type. All right. So if the difference in the electronegativity values goes from 0.0 to 0.4, right? Then that bond, for most intents and purposes, will be considered to be non-polar covalent, all right? So if you have two atoms bonded to each other, I'm trying to think of an example. Let's say a carbon bonded to a hydrogen bond. Let's look at that bond, right? If you were to go to the tables, let me see if I can find the table here. Okay, so according to this, carbon has an electronegativity value of 2.5 and hydrogen is 2.1, right? So the difference between them would be 2.5 minus 2.1. That's the difference in the electronegativity value. And that would be equal to 0.4. So therefore, this bond would be considered to be nonpolar covalent, all right? Because it falls within the range for that type of bond. Okay, if the bond difference, if the electronegativity difference between two atoms connected by a bond is from 0.5 to 1.7, then this bond is considered to be polar covalent, all right? So a good example of this is the hydrogen to chlorine bond. Hydrogen is 2.5 and chlorine, hydrogen is 2.1, my bad. Hydrogen is 2.1 and chlorine, let me see where chlorine is in the table. Chlorine has a value of 3.0, all right? So 3.0 minus 2.1 give you 0.9. So therefore this bond is polar covalent because 0.9 falls within the range here for polar covalent bonds, right? And then finally, if the difference in electronegativity values is equal to 1.8 or greater, then the bond is essentially ionic, right? So for example, sodium chloride, chlorine is 3.0 and chlorine is, let me see here, chlorine, sodium is 0.9. 0.9 here. That would be equal to 2.1. So therefore, the sodium chloride bond is ionic because 2.1 falls above 1.8, all right? So that's basically the criteria that is used to determine whether a bond, and let me just say that this is not a universal criteria. In different textbooks, you'll see different, slightly different ranges, right? But for our purposes, this is what we'll be working with, right? Non-polar covalent, the difference in the electronegativity values would be 0.0 to 0.4. For polar covalent, the difference would be 0.5 to 1.7. And for ionic bonds, the difference would be 1.8 or greater. All right. Okay. Any questions about this? Any questions?
Nope.
Okay. So continuing with the PowerPoint. Okay. So the next thing we're going to talk about is okay, resonance, right? So I alluded to this earlier, right? Very important theory, especially for those of you who plan to do organic chemistry. You're going to see that this theory plays a big role in terms of explaining some observations concerning organic compounds, right? You're going to learn, for example, why two compounds that may have, you know, slightly different structures, why one would have, for example, a greater solubility in water than another, why one would have a greater level of acidity compared to another one. I mean, there are several things that resonance can be used to explain when it comes to certain properties that are observed in organic molecules, all right? So what is this theory all about? Well, basically what this theory says is that whenever you have the possibility of a molecule or ion being represented by two or more plausible structures that differ only in a distribution of electrons, then the true structure, it will be a composite or a hybrid of them, all right? So that's a bit wordy. And let me try to explain that using the example of the ozone molecule, right? So what you're looking at here would be two structures representing the ozone molecule, all right? So you'll notice that the difference between these two structures, well, there are a couple of differences. One where, in this case, wherever you see the single bond, in this case, you're going to see a double bond here, and vice versa, double bond here, single bond here, right? Also, you're going to see that this oxygen, which has a negative charge, now has no charge on the other structure, and the opposite is true for this oxygen. Had no charge here, has a negative charge here. You'll also see some differences in terms of how the electron pairs are distributed. For example, this oxygen here has 2 lone pairs, while the same oxygen in the other structure has 3 lone pairs, and in this case, this oxygen has 3 lone pairs, and the same oxygen in this structure have 2 lone pairs. So there are differences between them, and we can get from one to the other by basically shifting this pair of electrons down here to form a double bond, and at the same time, this pair of electrons come here to give you the lone pair right here, all right? So basically, according to the resonance theory, if it's possible to have two structures being drawn like this, then the real structure is not represented by this structure by itself or this structure. The real structure is represented by a hybrid between those two structures, all right? And basically what this is saying is that each of these structures is not adequate enough to represent the true structure of the molecule of ozone in this example. And there are several reasons why this theory became necessary. Because when this molecule was looked at in more detail, a couple of things were discovered. Well, let me just say this, and this is something we're going to see later on. Typically what you'd expect is that everything else being the same, a double bond will be shorter in length compared to a single bond, right? If everything else is the same, that's basically what you'd expect. When scientists examined the bond lengths of these molecules, what they discovered was that this bond length here is the same as this bond length, which is not what they expected, right? They expected that this bond here would be shorter in length compared to this bond. What they found out was that this bond and this bond has the same length. And what they also found out was that the bond length in each case is somewhere between what you'd expect for a single bond and what you'd expect for a double bond, right? So basically that's just one piece of information that was gained, which indicates that each of these structures are not sufficient enough in order to represent the true structure of the ozone molecule. Turns out that the real structure is a hybrid between those two, what we call resonance structures, all right? And, you know, some people might have some difficulty appreciating this. So I oftentimes use the analogy of the relationship between a horse, a donkey, and a mule, right? And this is a biological example because a mule is a hybrid between a horse, and a donkey, right? So what that means basically is that the mule has some characteristics in common with a horse, and then it has other characteristics it shares with a donkey, right? It doesn't mean that the mule is sometimes a horse or sometimes a donkey. It just means that the mule shares characteristics with both of those animals, right? Well, the same is true in relation to the hybrid structures as it relates to the resonance structures. The hybrid structure has some similarities with each of the resonance structures that is used to represent it, all right? So that's basically the whole idea behind resonance, the resonance theory. One more thing I want to say here before I leave this page, and that is the whole concept of delocalization of electrons, right? Which again will be very important for those of you who plan to do organic chemistry, because basically, as I said before, when this pair of electrons comes here to form a bond here in this Lewis structure, this pair of electrons will be pushed out here, right? So basically, according to the resonance theory, this pair of electrons here is said to be delocalized, because basically what we're having here is that a lone pair of electrons from here ends up over here. So basically you have what we call a molecular orbital, which contains a pair of electrons, which is distributed from one end of the molecule to the other, from one oxygen atom to the other oxygen atom, all right? Again, as I said before, this will become important in organic chemistry. Okay, any questions about resonance and related topics? Any questions? Any questions?
So with resonance structures, do the electrons just vibrate back and forth?
Okay.
And
not quite. Basically, whoa, what's that noise?
Hello? Sorry, that was my ringtone. Hello?
Oh, okay.
Oh.
So
trash call, sorry.
Okay. So let's see here. Vibrate would not be the right word to use. Basically, if you remember, okay, so let me go back to something we discussed a couple of chapters ago. Remember we talked about the concept of the atomic orbital, right?
Yeah.
I remember we said that by definition, the atomic orbital is a region in space where the probability of finding an electron is 90% or greater, right? Well, the same kind of applies in this case here. Instead, we talk about a molecular orbital, right? And basically what we're saying is that the likelihood of finding the electron from here to the other end of the molecule is relatively high, right? So it's not a matter of vibrating. It's a matter of basically electrons are always moving, but you cannot tell exactly where the electron is at best, or in this case, a pair of electrons. You cannot tell where the pair of electrons will be. All you can say is the probability of finding the electron within a particular region along the length of the molecule is 90%. That's the best way, it can be described. All right.
All right.
Yeah. So that's basically the reasoning behind the resonance theory when it comes to the delocalization of electrons. Okay. Any other questions about this particular topic? Any other questions? Okay. Let's see what's next. Okay. I think this will be the very last thing we're going to talk about. Bond lengths. All right. So firstly, let me talk about bond order. Very simple concept. The bond order is basically a number that indicates whether or not the bond is single, double, or triple bond, right? So if the bond order is 1, that's a single bond. If a bond order is 2, that's a double bond. If the bond order is 3, that's a triple bond. All right, very simple concept. All right. Now the bond length is a distance between the nuclei of two atoms that are joined by a covalent bond. And some examples are shown here. So for example, hydrogen has a bond length of 74 picometers. Oxygen has a bond length of 121 picometers, and so on and so forth, right? Remember, 1 picometer, just to give you an idea of what we're talking about, 1 picometer is equal to 10 to the minus 12 meters, all right? So that's the picometer unit, okay. Now, it turns out that the bond length is a function of a couple of things. The nature of the atoms in the bond and the bond order, right? So we're gonna look at how the bond length is affected by those two things, right? So here we have a table. This table gives you different types of bonds and their bond lengths and their bond energies. We're going to talk about that. I don't think we'll have time to talk about this today, so that will be taken up in the next class, all right? So for now, we'll be focused on the bond lengths, right? So I want to point out a couple of things, a couple of trends that, affects the bond lengths, right? The first of which is the multiplicity of the bond, right? So basically, what you'll find is that the more bonds that you have between two atoms, the shorter will be the bond length, right? Which makes sense if you think about it, because with each bond, you have electrons that are shared between two atoms. And remember, the bond is an attraction between the nuclei and the shared electrons, right? So basically, the greater the number of paired electrons shared between the two atoms, the greater will be the attraction between the nuclei, the two separate nuclei and the shared electrons, and therefore the atoms will be drawn closer to each other. So if you look at, for example, this series here, the carbon-to-carbon triple bond compared to the carbon-to-carbon double bond, compared to the carbon-to-carbon single bond, you see that the trend is, as you see here, the shortest bond would be the carbon-to-carbon triple bond, 120 picometers. The next in line would be the carbon-to-carbon double bond, and then finally the carbon-to-carbon single bond, which would be the longest bond, right? So basically, the greater the number of bonds present between the two atoms, the shorter would be the bond. Same thing when you look at even between two different atoms, carbon to nitrogen. As you can see here, as you go from single to double to double to triple, the bond length decreases, all right? Over here, carbon to oxygen and then carbon to oxygen double and single bonds, right? Again, the bond length decreases as you go from single to double. And then if you look at the nitrogen to nitrogen, single to double to triple, again, the bond length decreases, all right? So basically, same thing here with oxygen. That's a single bond, that's a double bond. Again, the bond length decreases. So basically, the greater the multiplicity of the bond, the shorter would be the bond length, right? Another factor that affects the bond length is the size of the atoms involved, right? So which one shall I look at? Okay, let's look at these three compounds, or these three bonds, I should say, HF, HCl, and HBr, right? Now, of these, so the hydrogen is fixed, but the other atom is changing, right? So the bromine atom is the largest, followed by chlorine, followed by fluorine, which is the smallest. And if you look at the bond length, you'll see that for HBr, the bond length is the largest one because the bromine atom is larger or largest, and then followed by the HCl, followed by the HF, right? So basically, the greater the size of the atom, the greater would be the bond lengths, all right? Okay, you can see something similar happening if you compare, let me see here. If you compare these three, all right? Now you have to be careful here because remember, if you look at the periodic table, nitrogen is to the right of carbon, right? So therefore nitrogen is a smaller atom compared to carbon. Hydrogen is the smallest, right, compared to those two. So therefore what you'll find is that of these bond lengths, the carbon to hydrogen bond would be the greatest, right? Followed by the hydrogen to nitrogen, because nitrogen has a smaller size compared to the carbon atom. So it's, I'm sorry, I'm looking at I'm pointing to the wrong thing. The bond length here is 100 picometers for the H to N bond, and then for the hydrogen to hydrogen bond, that's 74 picometers. So basically, the smaller, or let me just say, the greater the size of the atom, the more longer the bond length will be, all right? Okay, so that's basically the bond lengths and the different factors that affect the bond lengths. Okay, I'm going to stop here because discussing bond energies will take a bit more time, and I don't want to start this topic and then stop in the middle of it. So that's it for today. Let me stop sharing, take roll. Okay, so today is the 15th. All right, so let's see who's here. Arias Rios, I don't see her. Barber is
I'm here.
Canon. I don't see Canon Chang. I don't see Chang Chavis. Nope. Clark is here.
Here.
DeGraff. Franklin. Han. Panic. Heron is here. Holland is here. Jurgensen is not here. Rees, not here. Rouse is here. Runnels is here. And Smith is not here. Okay, so that's basically it. Just a reminder, your test will be next week. And I'm feverishly working on your grading your quizzes so I can post the answer keys online, and I'm going to send you your graded work as well. Taking a bit of time, but I was hoping to get that done early this week, but I'm aiming for tomorrow to have that done. So you'll have that to review. Another thing too is that you may have seen the announcement I posted earlier today. I won't be available for office hours, which would be normally from 2 to 5 today. And that's because I have 2 events to attend back-to-back online, which will take up the entire period. So I'm shifting those office hours to tomorrow from 2 to 5, if you have any questions, all right? So I guess that's it by way of announcement. So unless there are any questions, that's pretty much it for today, all right? So I take it there are no questions. So enjoy the rest of your weekend, and I'll see you guys next Tuesday. Take care.
All right.